the first one I receive, I could say I received it, because I don't know what the time is yet. So I could say I received it at some time, which means it is x away from me. And then the second one I received, I say I must have received this at some time a few milliseconds later. So I could say it's x plus a milliseconds away from me. And then another one arrived just after that from this one. And I can say that one's x plus b milliseconds away from me. And because I know where these are, I can just basically find a solution that satisfies the geometry of all these different distances. And the only way it's slightly different to triangulation is because you just need one more satellite than you think you need because you don't know x. So there's just one extra term in the simultaneous equation. So basically, in order to get a 2D fix, you need 3D fix, you need 4 satellites. It's slightly different because you might think that in order to get a 2D fix, you would need 3 satellites, but very frequently with 2 satellites, you'll have if you just had 2 satellites, you say, well, I could be here or I could be here, but very frequently this point is sort of at walking speed on the Earth, and this point is at 10,000 meters per second traveling through the middle of the Earth. And so you can say, well, that's just a nonsense solution. So you can often get away with 1 fewer satellites than you need. But so the basic thing of GPS is they're just telling you what they think the time is, and you're measuring when these packets from them arrive. And from that you can figure out where you must be relative to the rest of them, and that's how GPS works. So it's quite simple. The really clever bit, I think, is how they actually talk to us on the Earth and how we receive them, which is a kind of a radio problem, and quite an interesting one. I will switch back this laptop. So I'm basically going to talk mostly in this talk about what the GPS signals look like and how you can receive them. I'm going to do it by programming, a mixture of diagrams and programming. I'm going to use a programming language called Python, which is quite simple, and hopefully, even if you've not done any Python, you should be able to sort of see what's going on, because it's basically just maths. It is just hopefully fairly straightforward maths. So I'm going to use this nice this lectern is wobbling around all over the place. It's going to be tricky. I'm going to use this nice web-based Python interpreter called IPython Notebook, and that should bring up a browser, hopefully. Yep. And then I start a new notebook. No, that's fine. Because everyone in this room has got all sorts of various different levels of familiarity with and how recently they did maths or whatever, I'm going to just quickly do a primer on some of the basic signal processing and maths that you might need. So the fundamental thing we deal with in radio frequencies is a sine wave. And a sine wave is just, it looks a bit like, I'm just going to draw a random one very quickly. So I'm going to define a variable called frequency, which we'll set at 2 Hertz. I'm going to make a little array of time. So all I've done with this linspace thing is say, make me an array of numbers that starts at 0 and goes to 1 and has 100 in 100 even spaces in between the two. So you can see that's just what time. It's just a list of numbers that starts at 0 and ends up at 1. So basically, that's going to be a second long, split into subsamples of hundredths of a second. And then I'm going to make something called a sine wave. Sine wave, which is going to be. Don't worry about precisely what this means just yet. I'll explain it in a second. So that's the sine wave. I'm going to then plot time against the sine wave. Okay, so all I've done is told this sine function to take the list of numbers between 0 and 100 and multiply them by 2 times pi times the frequency, and then save that as a new vector. So the sine wave actually looks like another another list of 100 numbers. So that's what this is. That's just having multiplied this lot together. So this is a list of numbers, and these things are constants. So I'll explain what 2 pi means, because it's an annoying thing that they often don't teach until late in school for some silly reason. So we're used to dealing with degrees for angles, but actually, if you take a circle, we say there are 360 degrees in it. So this is 90 degrees, and 360 in total. Actually, a more natural unit for mathematics is to say that there are 2 pi radians in a circle. So that means half a circle is pi radians, and the other half of a circle is pi radians. It literally just means the same thing. It's like Fahrenheit and Celsius with degrees and radians. So if I want to say my frequency is 2 hertz, that's 2 cycles per second, which means you have to multiply it by 2 pi to get the number of radians per second that's in, and that's just the natural units of sine and cos, which is what we deal with in mathematics. So this is just a conversion factor to turn what we understand as hertz into radians per second, which is what the maths understands. So just bear that in mind. Laptop. Right, so I'll go back to plotting something.
Yeah, I mean, the key thing is you can just put it over the 2 times pi times frequency, just put time, you'll get the same thing. If you're just putting it in
yes.
form that is convenient.
Exactly. So is that hiding behind? Yeah. Sorry, so there's that graph from before. So that's just showing, it's just a sine wave that looks like that, and it's all sort of something we've seen before. So, and just to emphasise that is a list of numbers, we can just plot it slightly differently and say marker equals 0 and line style equals none. So it really is just a list of numbers that we're just plotting graphically. But what we're dealing with whenever we do the signal processing digitally is just big lists of numbers that we move around the place. So that's all we're doing here. Let's go to my next page of notes. So we're sort of talking about receiving a hypothetical sine wave that is the carrier frequency of something that's talking to us. How do we actually find what that... If we've got some signal coming in and we don't actually know what it is, how do we actually look for a signal in there? Well, we can do... oh no, I didn't mean to do that. B. We can basically hypothesize ourselves. We say, I think there might be this kind of signal in this unknown signal that I'm receiving. How well does this unknown signal I'm receiving compare with my copy of the signal on the ground that I think might be in there? And a simple way of visualizing that is to just, let's say, we have some we have a sine wave of some frequency, and on the ground we have exactly the same thing, and we want to say I think this signal is unknown, and this is what I think it might be, so I'll just call that the guess. And we can say, what kind of mathematical operation can I do to see how well these signals compare to each other, to see if my guess is good, so I can get a score out for how good my guess is. And it's actually quite simple. All you have to do is just remembering these are actually samples, actually discrete dots. You can just multiply all the samples together. So, for example, when this is 1, this is 1. So when this is 0, this is 0. So the score is 0, and it's 1 there, and it's 0 multiplied by 0 there, and it's minus 1 there, multiplied by minus 1 there, which gives you 1 again. And you can go through for the whole bit of sine wave, just multiplying up all your guess with the hypothetical one, and add up the numbers you get at the end together, just to give you a score as to how well they agree. So if we try that, let's say I've already defined this thing called sine wave. Is that working? Oh, no. Okay. So I can define that as being the hypothetical one can be sine wave, and the one, let's just pretend I happen to have guessed exactly right, so I've got an identical local copy for sine wave. So if I just multiply the two vectors together, which is just going to multiply each element in the two listed numbers together, then add them all together, I get a score out of, say, 49.5. It depends on how long the data vector is or whatever. But because, I mean, about 50 makes sense, because if you recall from here, the lengths of these lists of numbers is 100 long, and they're sort of alternately 1 and 0, 1 and 0, 1 and 0, so it's going to be about 50. So we can do something else with sine waves. We can start a new cell. We can have this concept of the two sine waves might not be perfectly aligned. There might be a slight offset of one sine wave relative to another, and we call that phase. So I could define some kind of I can just plot an example. So I'm going to plot our first sine wave, and then I'm going to plot next to it the same thing as how we defined sine wave before, which is 2 times pi times the frequency, which as we've said is 2 for 2 hertz. And then you just add a little offset to each of the elements in this list. So say, for example, 45 degrees, which will be pi divided by 4 radians, because pi over 2 radians is 90 degrees, so 45 degrees is pi divided by 4. So we're expecting to see here, with luck. Yeah, so there's, we've just got the one, our main sine wave, and then another sine wave with a slight offset, which we just created by just adding a little offset each and every time we generate the new sine wave here. So we can have a look at how well we can have a look at how well these two correlate together, as in how well they compare. Times by, so same equation as before. So the score there is 35, whereas it was 49.5 before. So the score's a bit lower because they're slightly offset from each other. So they don't agree as well, basically. This is just this score, this process, which we call correlation, is just a metric for how well the two signals agree with each other, how similar they are to each other. What happens if you go completely out of phase, which would be pi, that's 180 degrees. The score is minus 49.5. So it's the same, but just negative, because in each case you'll get the peak of one will coincide with the trough of the other. So you get 1 times minus 1, which is minus 1. It's just a mirror image, basically. At some point, in fact, I'll do a few more shifts just to show you. We can get rid of this. We don't need that. So if we did pi before, which was 45 degrees, we got a correlation of a score of 35. If we did pi over 3, we got a slightly worse correlation still. If we did pi over, say, 2.5, which is even more shifted, the correlation score is worse still. If we go down to pi over 2, which is 90 degrees phase difference between the first sine wave and the second sine wave, the score is minus 1 blah 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 times 10 to the minus 15, which is an extraordinarily tiny number. It basically is 0, except for the precision of the computer calculations. So we've got a bit of a problem, which is that at some point, if we're looking for a signal of, say, a sine wave of 2 hertz somewhere in our signal, but our local copy of the sine wave, our guess of the sine wave, happens to be 90 degrees out of phase with the sine wave that's actually there, we basically can't see it because it's out of phase. So I'll plot that just to make it obvious. I'll probably have to close down this window first. Plot time. So that's plus pi over 2. Yeah, so that's basically the scenario that is our problematic one, because we're multiplying, when this is 0, this is 1, so that multiplies to 0, and when this is 0, this is at its peak down here, so that multiplies to 0. And basically all, they're just, yeah, they're completely in their phase difference is 90 degrees, or pi over 2, and the correlation doesn't work. The correlation score is 0 whenever that happens, so that's a big problem if we're looking for, say, a 2 Hertz thing. So what we can do then is, as a way around this, is to compare it to...
They are out of phase when the difference is pi.
They're in antiphase, but there's always a phase difference between them. I guess I'm just being sloppy with terminology if I say out of phase. I just mean there's a phase difference, and at some point, at some phase difference, the correlation score is 0 between the two. So we've defined the sine wave up above. I can make something called a cosine wave, which is just a sine wave. In fact, yeah, I'll do it like that. Times time plus pi over 2. Print cosine wave. So that's just another list of 100 numbers, but we've generated it so that it's 90 degrees out of phase with our sine wave, because we've just added a 90 degrees or pi over 2 phase shift to it. What we should see is that if we now, I'm gonna stop typing this x times y for the correlation, because Python has a built-in thing called correlate, which does exactly the same thing. So I can say print correlate of sine wave and cosine wave. And again, it's a completely minus 10 to the minus 15 is a completely tiny number, almost 0. So what we can do is what I'm going to do now is basically generate a bunch, a hypothetical received signal with a bunch of different shifts, and compare them to both get the correlation score with that received signal with both the sine wave and the cosine wave, and we can see what the relationship is between the correlation scores for a given signal to both the sine wave and the cosine wave. It should hopefully be quite instructive. So I'm just going to make a little vector called shifts, which will... so it's basically going to make a vector, 36 different shifts between 0 and 2 pi, a whole circle. So it's just a sine wave of different shifts like that. And then I'm going to say for shift in shifts. So that's for each element in this vector of shifts called shift. Plot correlate of sine wave and then correlate so this thing on this second argument in each case, this one and this one, is the hypothetical signal that we're receiving, which I'm generating each time around this loop. But each time it has a different shift, and the shift each time depends on it just goes through all of the shifts in this list of shifts. This English is not the best language for describing this sometimes. Whoops, that's not anything. And then I want it to be dots. This just means it's dots instead of a continuous line when I plot it. And I'll just make them all the same colour. And then what I'm just Yeah, I think what I've done in advance is because some of this is really tedious to type out. I'm making a slight, code. Talk snippets. I've just copied and pasted some of the really. Oh no, I haven't done that. That was silly of me. Okay, I haven't copied and pasted that bit of code. So I've written it down here. So hopefully, if this works, great. So what we've got is so it's drawn it a bit. Where's my laser? Oh, I can do it. So actually, the axes are 0 and 0 here, and this is the correlation score with the sine wave along the bottom here, and the correlation score with the cos wave along the top here, and then these are each of the given signals that we generated that's coming in with different shifts. So each dot represents the correlation score for one signal. So you can see that if I just print off shifts quickly, print shifts. So you can see that we start off with the first incoming sine wave we generate has a shift of 0, and that happens to be this one here. So you can see the correlation score is almost entirely in this sine wave axis, which is a score of 50, and basically 0 in the cosine wave axis. And then as you increase the shift slightly, you get slightly less in the sine wave axis and slightly more in the cosine wave axis. And as you increase the shift even more, you get even more less in the sine wave axis and more in the cosine wave axis. And although it's printed this on a rectangular thing, actually this is a perfect circle. And what it's basically showing you is that if I just draw a simplified example, visualizer. So this is sine, cos, the correlation scores in each axis. You get a circle. It turns out basically that this length is the same for every single incoming signal, but the amount of it that is in sine and the amount of it that is in cos changes depending on the shift. But because this is always, these are basically just triangles that we're making here. So we have some amount of sine between here and here. We have some amount of cos between here and here. And this length will always be the same. And this is just a right angle triangle, which we know from Pythagoras. So we can say that the total correlation score, which is the length of this line, is always the same, and it's just from Pythagoras going to be the correlation score with the sine, which I'll just call sine for shorthand, the correlation score with the cos, our local cos wave, square rooted. So so basically, if we generate two signals locally, one in phase and one at 90 degrees out of phase, and correlate with both, and then take the length of the triangle that they make, we get a score for correlation, which is always tells you how much signal there is of a given frequency. So I'm just going to make a little function that can automate all of this for us. So signal